Hello, we will be presenting our neural rendering final project, which looks at augmented reality applications with object insertion. Our project motivation focuses on the perception and integration in augmented reality. What makes augmented reality such an interesting application is the ability to interact with the real world, to be able to see both the real world while also a virtual object. Background environment and neighboring colors impact how we perceive color and lighting. So when we think about the usability of augmented reality, we see how the perception of these virtual objects are greatly impacted by the environment, which can even hinder and alter our ability to perceive and understand the virtual object we're trying to look at. With better integration of our environment, we can make AR more usable and immersive. Thus, the virtual objects won't be difficult to perceive and understand, and we can create more advanced applications such as surgery, robotics, and assistive technology where objects are needed to be inserted, and we don't want the environment impeding on our understanding and our visualization of that object. Additionally, because we are looking at insertion in augmented reality, specifically in a HoloLens headset, it is important to be able to understand the environment from this augmented reality device. Thus, our project has two main goals. The first goal is to be able to obtain 360-degree input images using an AR device. In other words, we want to be able to scan our environment with the HoloLens device rather than a separate device such as a phone. Then, given this input data, we would like to insert the virtual object of interest with lighting to appear that it belongs in the environment.
Our first step toward obtaining 360-degree images is creating a color point cloud using the Microsoft HoloLens 2. This augmented reality device has a normal RGB camera like you use with a phone, as well as a time-of-flight depth sensing camera, which allow us to create a virtual rendering as if it appears directly aligned to the real world. These cameras run on separate threads, so we temporally and spatially synchronize the two streams together into a real-time point cloud rendering. Since we are limited by the camera's field of view and a single perspective, we must build up successive frames to scan an entire environment. The AR device relies on tracking cameras to anchor itself within a space for each application session. To preserve the anchoring between sessions, for example, see the lighting from the same room in a different session, we anchor the points relative to a QR code, though any tracking marker will do. Here we show the capability of tracking a QR marker directly in our application. To avoid the overlapping of points for each scan frame, we implement the spatial partitioning algorithm voxel hash to check for colliding points. The first step is to transform the floating point world coordinates into integer world coordinates through multiplication and rounding. Next, we compute a hash key function to see if this point has already been scanned. If it's already been scanned, we continue on, and otherwise, we use the point for our world-aligned mesh, which is also anchored to the marker origin. Computing this many points on a mobile AR device is expensive, so we want to utilize any available cores on the device or our CPU-bound calculations. We use C#'s concurrent library to efficiently check for collisions in a lock-free way. For constructing the 3D scan, the user may choose from 4 possible modes. The default static mode renders all non-colliding points. The dynamic mode allows for colliding points to be replaced by the latest frame. And optionally, the occlusion effect, or shadowing, has an origin at the start of the scan, like the starting head position when you press start for the scan, and ignores points that are not visible to the origin position, creating a shadow-like effect on the occluded objects. For an end-to-end user experience, we display the 3D points as a guide for when the environment scan is complete. Impressively, the rendering technique is able to handle 4 million vertices, but a smoother rendering could be done remotely, away from the mobile device. We also showcase a cube that can transform the point cloud as it acts as the origin. Scanning the room takes less than 10 seconds and only requires the user to look around and look at areas in the room that are not yet covered by the point cloud. When the user finishes their 3D scan, we then project it to an equirectangular or panoramic image through projection methods. The first is a spherical projection for translating 3D world points as Cartesian coordinates. Finally, we perform cylindrical projection for mapping the Cartesian coordinates to a 2D image. The spherical projection is simply normalizing points relative to the origin so that they have a radius of 1 meter. These points will also have an associated color with them. In this code snippet, we show our solution toward building an equirectangular image from 3D points in StereoKit's world coordinate system. We notice that running this algorithm in parallel with a single shared lock between threads, just for simple assignment, runs up to 2 times faster than normal iteration. After the pixels are set, we encode the bitmap to a JPEG image and save it to the device. Here we see the outputted panorama with color pixels represented as 4 bytes, which is fairly common for many mobile cameras.
Now that we have the 360-degree image, the next step of our approach is to generate high dynamic range images from the collected low dynamic range images. To accomplish this, we use ExpandNet, a neural-based method for creating HDR expansion from LDR content. ExpandNet accomplishes this by using a deep convolutional neural network which attempts to reconstruct missing information that was lost from the original signal. This can be due to quantization, tone mapping, or gamma correction. The added information is reconstructed from learned features as the network is trained in a supervised fashion using a dataset of HDR images. We run ExpandNet on a PC with the equirectangular LDR image as input. After ExpandNet generates our HDR image, we manually upload it to the HoloLens 2 document folder. But in the future, we plan on automating this process through connecting the output of ExpandNet directly to the HoloLens. You can see here how ExpandNet performs on a traditional LDR image. The right image is tone mapped to HDR output of the equirectangular LDR image, with the light sources estimated accurately. The wooden floor in the 2 images is a good reference for comparison. In the next step of our approach, we insert a 3D object into the scene with respect to a QR code as a spatial anchor. This 3D object is selected by the user through a virtual user interface. The user can then manipulate or interact with the virtual object. Then we create a simple user interface for the user to switch between the 2 modes, editing and viewing. The user has the ability to start a new environment scan, toggle the point cloud on or off, or project the last scan onto a panoramic image to save for later. The user can open the HDR image in the application and toggle between images to see the changes in environmental lighting on the 3D objects.
Thus, we have successfully met our project goals in being able to scan the environment using the HoloLens to get a lighting profile and input data that is then used to virtually light an object such that that object looks like it belongs in the environment of interest. Future work would be to form a better method for evaluation in determining if this lighting of the virtual object is actually accurate and a good representation of what the object would look like if it was physically in the environment. To do so, we would want to conduct the following experiment. The first step would be to create a ground truth that we can compare our virtual object to. We would render the virtual object in the environment of interest using NeRF so that that object has the correct lighting profile from the environment. The next step would be to create a sample for our experiment where we render the virtual object in a more simple lighting using NeRF. So it is different lighting from the environment of interest. Finally, we relight that sample object to fit the environment of interest, so we are using the HoloLens headset to light the sample, and then we compare the ground truth with the sample. We would evaluate how close our sample is from the ground truth by using 2 different metrics such as the learned perceptual image patch similarity or the color mesh distortion measure, and this is just determining how close our lighting prediction is to the actual ground truth that we collected using NeRF. An alternative metric for evaluation would to not perform something as quantitative but more qualitative with a user study, asking users to scan an environment, insert a virtual object, and articulate if they felt that virtual object did belong in the environment and if they felt that the environment in any way hindered their perception of the object or if the object did feel like it belonged in that environment. While this is not as quantitative and maybe not as concrete, this also would give us a good understanding of how people are perceiving our objects and might be an even easier method for evaluating our tool. Ultimately, we have successfully created a user interface for both scanning and rendering image, and our next steps would be looking at evaluation. Thank you.